So how have you been this past week? Did you survive the cold?
Somehow.
Some now, yes. It has been quite something, isn't it? The in any case, thank God we are out of it and we're ready to move forward. So what I wanted to tell you is some things about our class. So obviously we missed a week, but what I try to do is to try to remove material from the class that I consider, of course, everything is important, but not as important as other things that we need to cover. And then I also moved the midterm. And so I sent you an email. So please make sure you look at the emails I'm sending as announcements. If for some reason you have not seen the email, you can get on Canvas. And then from there, you can see the announcements that I've made. So about midterm, as you know, traditionally in the spring semester, we have a week, a break rather, 1 week break, which this year, because of the virus, the university has decided to reduce to 1 day, which they call the reading day. And that's on a Friday. Now, what I decided to do is that I did not want to give you anything after that day, assuming that you will need some time to rest. So I put the midterm on Wednesday before that 1 day that we have as a break, rather. We call it reading day, but it is really a very, very short break. And if you notice, the material that I've put for that week is we're going to have reviews on Monday and during office hours on Monday. And then I will also arrange to have some time on Tuesday for like a review. And the previous week, we are going to do the same thing. So we're going to have enough review for the midterm. The finals are scheduled by the university, and the finals have remained the same on the basis of what information we received from the provost office. So that's where we are. As you also have seen, all the homework has been moved by a week. It's like this week did not exist, rather. And so you're going to have until this coming Sunday to late at night, 11 p.m. to submit the homework. So that's where we are. And I would like to hear any questions or comments you may have. Do you have any questions of me? You can email me. And as if you have any particular questions. So since I'm talking about the midterm, it's going to be everything open. You know, as I've mentioned, it's going to be on Zoom. All of the exams, midterm and final, will be by Zoom and for everybody. And well, so those who need extra time, they will speak with me and they will get either extra time before, so you will start before everybody else or after, depending on your schedule. I really don't have a preference. If for some reason, any one of you has a valid reason not to take the exam at the time, I hope not too many, because then practically I will need to have a separate exam, and that's not good for either one, you know, to have separate exams, because I cannot make them equivalent, as you know. I mean, it's practically impossible to develop two different exams and make them equivalent. But so if a few of you have some serious issues, then please call me anyways ahead of time, as soon as you know. That would be good. Any other questions with regards to our schedule? Okay, so this week we will continue with a concept that is very important, and I will just share my screen for a moment. I don't know whether I share screen, start. Okay, and I'm going to my notes. And so today, as you will see from here, we are going to talk about the electric potential. I'm sure you have seen this before. It's not a totally new concept. We've seen it different times, but obviously now it is an important one for our class, and we're going to get into the discussions about the electric potential. But I wanted to remind you, as I said before, that a lot of the things that we see in electrical engineering are things that we have seen in life multiple times. And the important thing is to connect them. So you will be able to remember those things just because you have connected them to something that is familiar. And that's how, we all learn. So the electric potential, the word potential has been used multiple times. We use it in everyday life, isn't it? So when I say that my son has potential, or my daughter has potential, what does this really mean? In your mind, when you hear me saying that, what would you understand? Can somebody tell me?
Potential to do great things in the future.
Yes, it has the capability, rather, all right, to do great things. Absolutely. Does that mean that those things will happen? Not necessarily, but it means that the person, or whoever, we can say that this land has potential for development. All right, so we see a piece of land that has a nice view, has hills, and we say that. Does it mean that it's going to definitely happen? Not necessarily, but it means that given the opportunity, it can become something great. Or that my son or my daughter, given the opportunity, or assuming that they will take the opportunities, if there are any, they can do great things. Same thing with electric potential. Potential here, it means that given the conditions, we can have a strong electric field. All right, so that's what it means really. And given the conditions, especially in circuit designs, it means that we can have a strong electric field and we can utilize it. So that's the electric potential. It does not mean that something is definitely happening. It means that a device that we have could produce a strong electric field if we place it in the right circuit. That's all it means, all right? So same kind of meaning, but of course, the meaning has now been translated into electronics or into electricity. Could be to a lot of other electrical related things. Now, mathematically, to express something that can happen in the future, all right? So we talk a lot about things that can happen in the future. But mathematically, to express something that can happen in the future, what kind of mathematical manipulation do we incorporate to talk about the future? What allows us, from everything that we know mathematically, to talk about to mathematically rigorously talk about something that can happen in the future?
Probability.
A derivative. Okay, a derivative. A derivative is something that allows us to talk about the future or the past, as a matter of fact. And why is that? Because how do we define derivatives? Say, let's take a derivative in terms of time. All right, so I'm sorry, I have to. So dt, say, of a function phi of t. How do we define that? Let's assume that we are at time t naught, all right? This is present. And t1 is future. T minus 1 is past. All right, let's use that. So in using the future now in reference to the present, this derivative can be written as phi at t1 minus phi at t naught divided by t1 minus t naught when t1 goes to t naught. All right, that's how we define derivatives. That's why a derivative in reference to present, here, it gives us an opportunity to talk about the future, all right? And that's why we use people, when people thought about the capability, as you mentioned, to be expressed in some form of a field of energy in the future, they used a derivative to express it mathematically here. Now, in this particular case, because we don't have time, all right, so granted, time is not part of analysis at this point, obviously, because we're talking about statics. But we have 3 or 2 or 1 dimensions to look at, all right? So we are still performing within a space. So everything that we talk about is in space, but in space also you can consider that if this is a one-dimensional space here, and this is where I am now, this is where I will be in the future, and this is where I was in the past. All right, so you can translate it like this still. And therefore, a derivative here will tell me the following. If I were to that an electric field in x1 is nothing else but this function, which we call potential, at x1 minus potential at x naught divided by x1 minus x naught when x1 goes to x naught, very close to x naught, but above x naught largely. So practically what you see here, we have found a function which we call potential that, given the conditions, can produce a strong electric field, depending, of course, on how large the derivative is. Okay, when is the field strong? So let me, in fact, plot here, if I may, the potential. So what I would do here, let's assume that I have the potential V of x, and I will show it here with red. Okay, and I will have the potential here at this point is going to be this, V of x naught. And let's assume that it's here that V of x1. Okay, and in fact here, since I'm doing this, I will go to a new page for a moment because I would like to write a few more things. So I don't want to, so I will take this, I will cut here, and I will go to a new page here, add page. Okay, so now we go here and I will paste it. Okay, so now that's where we are. Okay, so let's assume that we have 2 situations. One is where Vx naught and Vx1 is one function. And the second one is with green, This is Vx naught. And this is Vx1, all right? So in one case, they are connected with this red line, and in the other case, they are connected with this green line. And tell me now, which of the two cases has the potential to produce the highest electric field?
The green.
The green, the one where there is the highest variation, all right, of V, according to this one. Exactly. So now let me do something else to ask you. Let's take the green and I plot the green along the X. So now the green along the X looks like this. Okay. So now I'm doing the following. Tell me, if you may, this is V, all right? So this is V of X. What are the points where V of X will have the least well, V of X is going to produce the least electric field, the areas around which V of X is going to produce the least electric field, or the points, say, or the small areas. So I'm not talking about the whole thing. So let's assume if you were to identify areas that look like this, all right? Let's assume that this is an area. I will put points here so we can talk about it. So this is a point A, this is a point B, this is a point C, D, E, F, G, H, I. Okay, where are the points where we have the least capability or potential to create an electric field?
Point D and I.
D and I, exactly. So D and I least, all right? Where are the points of the highest potential to produce an electric field?
B and H.
A, oh, B and E, which one did you say?
I said B and H.
B and H. If,
ACEG.
yes, it's, so here, if you take a small area, let's take a small area, like this small, all right? And I go around here. The values are the largest, but what I'm looking at is the change of the value, not the value of V of X, but how fast it changes. That's what, all right, that measures the derivative. So does the field change very fast at B and H? What do you think? No. Where is the, excuse me, go ahead.
Sorry, I was just clearing my throat.
Okay. So where does the field change the fastest?
At points A, C, E, and G.
Exactly. So the field changes fastest at point A, C, E, G, all right? Fastest. And B, also F and H is the least. And why is that? The value is very high. But if I were to go here in this area and look at this area very carefully, what I was going to see, I was going to see something like this. All right. That's how this area is going to look like here. It's going to look like this. There is no fast variation. All right. As a matter of fact, up here at B, at H and F, the derivative is 0. So practically, if this is a V of X, the highest value for an electric field, it will be at the points where the derivative changes the fastest. So here, here. Rather, the derivative has the largest value. Here, here. Okay? Do you now agree with me? That's by the definition. So the points A, C, E, and G have the highest potential to produce a strong electric field. That's what is interesting. So that's the other thing, all right, in terms of careers. So let's talk a little bit about that, because you use that. I mean, that's what I'm saying. This seems awkward here, but I bet you anything that you use this in your regular discussions. Let's assume that I'm looking at somebody's career here. Okay, let's assume that I'm looking at Elon Musk, and I'm trying to project his career. All right, so obviously when he was very young, it would be here, and then there was a point, and you can measure it in money, for example, or something else, and now he's here. I mean, how much more can he make? All right, the guy is probably the richest person in the world. Where was his biggest potential? Is it now, or was it before?
As a child?
Here, yes, exactly. Starting at this point, and just before I came to the top. And then I will tell you something else. That was his biggest potential. Now he's rich, but the potential is not what it used to be before he became that rich, all right? Or became that successful. So there is this is how we use it really. I mean, when I will not say now that Elon Musk has potential. I will never say that. But I'm sure if I were his boss when he was very young in age, I would say this person has a lot of potential. All right. So now there is another thing I wanted to tell you about potential and about how the brain works. And that is going to tell you why people who have a lot of money, like Elon Musk, they want to make more. Because a lot of times I was thinking, so these people have so much money. Why do they go so anxious about getting more? I mean, what is the big difference between 180 billion and 190 billion, 195 billion? I mean, I don't even know what it means, to tell you the truth. But here is how the brain works. The brain cannot measure absolute value. The brain cannot appreciate the value at the one level, but the brain can measure differences. Okay, so our brain can measure the difference between these 2 points because of near and long-term memory. The brain, therefore, cannot say, oh, I'm here, therefore I'm good, whatever that may mean. The brain thinks, is this point bigger than this one? Is this point bigger than this one? Or is this point bigger or less than this one? That's what the brain measures. So if you are at a plateau in your life, and you need to remember that, so you have to work against it practically if you want to be happy in your life. If you have succeeded, like in my age, if you are very successful and you are up here and you have achieved all of this, don't allow your brain to tell you, I am here now but I was there before, and therefore the difference is very small. And so I need to really go on another one like this. Why? You need to remember that your brain measures that. While you were up, it was measuring this and would make you happy. The moment you are up here, it does not understand that you are up here compared to down there. The brain will feel equally unhappy up here and down there. And because the brain measures the derivative, and that's by evolution. That's how we have been made, because, and that's why we make progress, as a matter of fact, as a species, all right? But that's, you need to remember that. So we need to remember that the brain cannot measure absolutes, but derivatives. And people only feel happy if that derivative is positive. So it does require a lot of effort to be content with what you have and to appreciate what you have, even if your derivative at some point in time may not necessarily be very high. So that's what I wanted. This is now my advice as somebody who is 3 generations older than you are. But it's very interesting on how we measure things. We measure differences. And in any case, removing now this.
Professor?
Yes, go ahead.
Is the electric field at D and I less or the same as the electric field at B, F, and H?
Okay, so it could be the electric field and B and I can be higher or lower, depending on the conditions, depending on where it started, all right, and where it's gonna end. The derivative by itself does not give you this information. What is going to give you information of whether the electric field is higher or lower are some constants that you are going to have. And the constants, of course, may change depending on in real conditions on the boundary, what we call the boundary conditions you may have. So I will not be able to respond to your question and say that the potential at A will be the same with the potential at I, or I mean a field, excuse me, the field at A could be the same with I, or the field with A can be the same or different than F, and unless I know more about the problem. Okay, so you will not be able to know the exact value of the E unless you know the boundary conditions. And depending on how complex the problem is, the constant can be a function of x2. And you may have another constant. All right. So you don't necessarily know. But you know where you have the potential to grow the value of the field, where you have the potential to have a growth in the field, all right, where, I mean, in fact, if you remove this for a moment and you leave only a D, don't want to complicate things. If you, if you only leave a D, for example, or let's assume that you have that one. If you had that one, let's see how that would go. So the electric field, let's assume that it starts at some point here, because I would like to respond to your question. I don't want to leave it ambiguous. Let's assume that it goes there. What happens? Depends on the derivative. So the field here, of course, it has a negative sign, but okay, let's assume that you're looking at the magnitude, all right, of the electric field. Forget about the negative sign in front of the derivative for a moment. So it goes here from the initial position here. It increases, all right? So practically, can I do the following? I don't want to be inconsistent or be confusing. Let me take some time to answer your question because it's a good question and I would like to answer it. Let's even take the negative side. Okay, so we start at this point. Oh, this point is the beginning. So let's assume I start at this point now. Let's assume for a moment my electric field was 0 in the beginning, all right? I have to make an assumption. All right, Now, the derivative here is positive, it goes up, but has a negative sign. So the electric field in whatever, the sign shows direction. Let's assume that it goes, we'll take the direction, okay? So the field, first of all, goes, let's assume it has a negative direction and starts growing, all right? And then it goes to maximum value here. And then the derivative goes negative, so here it goes positive. So it starts growing again, and then it stays constant. And then it goes negative again, and then it goes up, well, let me see. Goes up. Goes like that. So what happens is the electric field, in this case, because of the negative and positive derivative, follows kind of a similar kind of thing, but the maxima for the electric field will be the so the electric field will in fact, let me erase this because I think I did not do it right. I apologize. Let me erase it. Yeah, because the derivative, I made it look constant here. Okay, so here, the derivative is positive, but if the derivative is constant, then I think, assume the derivative is constant. It does not have, so it's constant here. It's a straight line, all right? So I need to be more precise. Straight line here, then goes like that. Then straight line here. Let's assume this is a totally straight line. Then goes like straight line here. So to simplify, straight line here, okay? Like that, straight line here. Then like this here, straight line here, and like that. Let's do it like this, all right? So it's simpler for me. So here is, if it's a straight line, the derivative is everywhere, the field is gonna go like that until it goes to B. So from here, it goes to B, B here, A here. From A to B, the value of the electric field is constant. And then it's here, constant. And then it is 0. So let's assume it started at 0. So it's 0 here. And then it's negative. If it's positive here, if it's positive there, it's okay. Okay, because here there is negative, but with a negative, it makes it positive. 0 here. Negative, yeah, negative here with a negative sign. 0 there. Positive here. 0 there in H. Positive here. And 0 here. If I make the field lines, straight lines, that's how it looks. Do you see why?
Yes.
Okay. Now, I don't know exactly, depending on the derivative, how much the value. Here is 0. I know, because this is flat. I know it started at 0. Everywhere that is flat is 0. Even in this should be 0 down here. Where is 0? 0 is here. Okay, so this one is here. That's a good example. I suggest you try to do it yourselves and see everywhere that the derivative is 0, the field is 0, assuming that it started at 0, right? And assuming that the lines are straight. Because if the derivative changes, like I had it initially, like lines that looked straight, but they were not. So you're not going to have this kind of performance for the electric field. But assuming that all of these lines are straight lines here, here, all of these are straight lines, not like circles and stuff, straight lines, then practically the field is like this. And this is B. So this is E of X. And the other is V of X. Okay? Is that clear now?
Yes,
Thank you
for
for asking me that question, because that clarifies a lot. I think this is a very nice example to see. All right, thank you. All right, so now this one, what you're gonna see is that on the basis of the definition of V, then you can write that the V, which is the potential, of course, is an integral of the electric field. All right, from here, from the derivative, we know that the derivative results in an integral. And as a matter of fact, by remembering the definition of the divergence, in fact, of the gradient, excuse me, this is a gradient of a scalar function, then you can find the electric field as integrated from point P1 to point P2. And what does it say is the following. If I now define two arbitrary points, P1 and P2, and I connect them with an arbitrary line, then the line integral of the electric field between points P2 and P1 is constant, independent of the line that you have selected. That's all it says. All right. And the line integral of the electric field, E dot dl, between points P2 and P1 is going to be nothing else but the difference of the potential in these 2 points. And how do we call this difference of the potential? How do we call this? We call it a voltage between points P2 and P1. Is that right? This is the voltage, V2 minus V1, which is the difference between 2 potentials, is the voltage between these 2 points. So for example, when you have a resistor and you say that I have a voltage VR between the 2 ends of the resistor, it means that the difference, if the current flows like this through the resistor, it says that there is on the left of the resistor a higher potential than the right of the resistor, which creates an electric field. And that electric field forces the free electrons to flow through the resistor, and they create a current. All right? So the voltage across the resistor is the potential difference, the difference between the 2 potentials, potential at point at the left. From that potential, you subtract the value of the potential at the right. And that voltage difference is what creates the electric field. And the electric field always goes from the positive potential to the negative. And the electric field moves these electrons and creates the current. Okay?
Professor, why are there negative and so E equals negative gradient voltage?
Okay, because in reality, there is a convention we are using. Okay, so practically it says the following. And I will discuss that later. When there is a flow of electrons, it's a convention. And why we are using this convention? Because the current, I, is created by what? By the flow of charges. In a metal, if this is an electron, what is the charge of an electron? Negative. All right. And what happens when an electron is moving from one direction to another? If you have movement of negative charges, if the electrons move like this, what do they create in their process? When they move right, they will leave a hole, which is going to create, which is going to move left. Why is that? What is a hole? The hole is a lack of an electron. Okay, so practically, when you have an electron that moves right, creates a flow of negative charges, which means that there is a flow of positive charges. So practically, what happens in the resistor, when we show I going like this current, practically the electrons flow like that. The electrons flow like this. For the electrons to flow like that, that means that the electric field that applies to them goes like this. And if the voltage it has to be higher, of course, on one end than the other, like this, then practically the electric field in reality applies in the opposite direction on the electron. So it's a matter of convention. All right, is that clear why we have the negative? Is how the electric field applies on charges and in what direction the charges go under the electric field that is present. That's the bottom line. So practically we did all of this. We did all of this for one reason. So the electric field, that's what the only thing you need to remember, that the electric field only starts from a positive charge and goes to a negative charge, like this. All right, and positive charges, where there are positive charges V1 is higher where there are negative charges V2. So V1 is higher than V2, and for it to go from V1 to V2, and practically to have an equivalent of plus charges towards starting from plus charges going to negative charges. So the whole thing is a convention to be able to accommodate between the electrical circuits and then the conventions we've used for the electrical circuits and the voltages and the charges that flow to create the current, which are negative. So we always consider the current to be the direction of the positive holes, while in reality, the electrons flow along the opposite direction. Is that clear enough? So it is a convention, mathematical convention. Okay. I'm sorry if I cannot give you any more physical meaning to it. Okay, so now the one thing is what I want you to remember. So we have a perfect conductor. What is the characteristic of a perfect conductor? What material do we call a perfect conductor?
The material that has less resistance.
Yes. And what are the less resistance means? And what are the, excuse me, yes. And what are the charges that flow in a perfect conductor? The free electrons. A perfect conductor is a material that has lots of free electrons. What are the free electrons? Are electrons, you know how every atom is, it has a nucleus, and then it has a cloud of electrons, lots of them, depending on the material. Now, the electrons, each one of them is at one orbit, according to the Bohr atom representation. In reality, it's a cloud, but let's assume that we consider every electron to have an orbit. So every electron has an orbit. The ones that are closest to the nucleus are the most tight, all right? The closer you go, the electrons are negative, the nucleus is positive. So the closer you are to the nucleus, the stronger the forces, electric forces that keep you there. But the outer electrons, which are at the outer orbits, have weaker forces. So even if a little bit of heat gives them enough energy to get out of these orbits and start running on their own. All right, so that's why when you hold the metal and the metal feels cold. All right, why is that? Because the heat is absorbed. A plastic, if you hold it, and stays warm, because the electrons do not move, do not take the heat and move away. They stay there, all right? They are not free electrons, not like a conductor. The conductor always feels cold when you touch it. So unless you have tremendous heat, obviously, that's a different story. But the electrons then start moving. So if there is a conductor and the electrons move freely, then what happens? The moment you have an electric field somewhere applied, the electrons is going to go from one point to another in almost time zero. Which means what? That eventually the electric field or the potential of this metal is everywhere the same, meaning that because the electrons flow so fast, there cannot be a potential differential that builds. Practically, it's like you have a zero field, all right, inside the conductor. So the field inside the conductor is always zero. Is that clear why the field inside the conductor is always zero? Because again, the electrons are so loosely attached to, they practically are free, all right? And then they can move wherever they want. So there is always equalization. If there is in a very short period of time, when the electrons move from one point to another, they equalize the field everywhere. And eventually, after they move, they stop in one position that is equilibrium. So in the equilibrium, and equilibrium means zero field. In equilibrium, nothing moves unless you add some energy. And again, in time, very short time, it goes to another equilibrium. So always in a perfect conductor, there is equilibrium because of the free electrons. And therefore, the electric field inside the perfect conductor is always zero. Do you have any questions? Is that familiar? Is this a familiar concept with you? Now, the other thing that I wanted you to also remember, and we will continue with that next time, is because the electrons in a conductor move so fast, if there is an electric field, if you have two conductors like this one here, one conductor is this one, perfect conductor, and the other conductor is this one, another perfect conductor. And then you apply an electric field in between. Practically, you put one conductor at one voltage or at one potential, if you like. You put this one at potential 1, you put this one at potential 2, and the two potentials are different. All right, so if V1 is higher than V2, so practically you have the electric field to be created, and it's like that. And you have all of the positive charges. So practically what happens if you put two metals at the potential difference? All of the positive charges will accumulate, meaning all of the electrons will leave away. All of the electrons will go out and they will leave positive charges that accumulate on the surface of this metal conductor, and all of the negative charges on the other end, they will come to face them. So practically, there will be a layer of negative charges below, electrons, a layer of positive charges above, and they will establish this electric field. And that's what happens when you put two conductors against each other. Now, if we reverse the situation and we have now the pink to be a conductor, all right? So we have the conducting slab is here, as you see, that's what they're trying to explain here, is that the electric field inside the conductor is 0. It's canceling out. And that's what in fact shows in here. But I suggest, without paying too much attention to this, just use the picture here to remember that the electric field inside the conductor is 0. So the total electric field inside the conductor is 0. And that's what, in fact, it gives you this result. And that's what you have to always remember, all right? Because the electric field inside the conductor, and I will finish with this, is 0, then the only way outside of the conductor is for the electric field to start at a perpendicular position. Why is that? Because if I have a conductor, let's assume that I have a planar conductor. Since there is no electric field here, the electric field has to look like this. Why is it like that? Because if the electric field looks something different, if the electric field was like this, that implies that the electric field on the surface of the conductor will have a horizontal component. But the horizontal component cannot exist because anything on the surface of the conductor or inside the conductor is 0. So that implies that you cannot have a field like this. That implies that the field can only be like the green one, vertical to the conductor. All right, and that's what you see here. All of the field lines, if you have a metal sphere, all of the field lines outside of the inside is 0, the electric field everywhere. Outside, all of the field lines start at a perpendicular position to the surface. And the same thing you see here. So look at these shapes very carefully to see exactly how it is. All right, I would like you to spend a little more time to observe this shape, and we'll start with that next time. Any questions? Okay, so I'll show you before you go. I have a, let me see. Okay. All right, so if we go to the home page for a moment, and we go to the top hat, I have an exercise very similar to the discussion we had in class. Why does it take me there? Okay, let me do it from here. Okay. So let me go back here. Okay, here. And, have an old email. Apologize for this. And then it's here. Okay. Well, anyway, I will make it. Let me try the other one because I don't know why this creates all of these problems. Oh, because I need to stop. Stop. Okay, so here. All right. This one, how do this can I share the screen, share screen. Okay, so if we go here, all right, so exercise. Okay, this is what I will have for you for today. So that gives you the electrostatic potential in a region as a function of a coordinate x. And they want you to say where the field is going to be the strongest. So it's very similar to what we did in this class. All right. So I will initiate that. And I will assign it. All right, so you will have until Wednesday to do this exercise. Okay? All right, so we have office hours today. You can join me anytime between 4:30 and 6:30. Any questions?
I have a question regarding the perfect conductor.
Okay, so I will see you either later today or on Wednesday. Take care.